Hey, it's me, it's your pocket tutor, and today we're going to talk about velocity. We will start by understanding what's the difference between speed and velocity. Then we will try to describe the motion of a rigid body, seeing also different types of simple motions, and then we will see how to compute the average velocity of a body. Finally, we will do a couple of exercises just to understand better what we're talking about. But first, what is the difference between speed and velocity? Why in physics is more common to talk about velocity and not speed? Well, speed is a scalar quantity. It refers to how fast an object is moving. So when we are describing the speed of an object, this is a scalar quantity. And we're just saying how fast something is moving. But velocity instead is a vector quantity, and it refers to the rate at which an object changes its position. What does it mean? Well, let's consider this bird here, and let's say that it is flying at a constant speed of 20 kilometers per hour. This means that its speed, this scalar quantity, is constant, but the velocity is continuously changing while it's moving. Because let's say that it starts with this velocity, v, that is a vector quantity. Once it moves to this point here, its velocity will change the direction. Even though the intensity is the same, because the speed describes the intensity of the vector velocity, the vector velocity is changing continuously along all this path that the bird is following. So, as you can see, the vector is always changing direction during all the flight. So velocity is a vector, therefore it has a direction and an intensity, while the speed is a scalar quantity, so it only has a value, but it doesn't have a direction. In order to more simply describe the motion of a rigid body, we can use the same simplification that we've seen when we talked about rigid bodies, that is the point particle. If you remember, the point particle is an approximation that we can employ when we are describing a body that is much smaller than the environment that we are considering. So when we're talking about motion, we can use the simplification or the approximation of a point particle when the body is traveling a distance that is much bigger than the body itself. Like in this case, if we are considering the Cybertruck that is moving along this racetrack, we can consider it, or we can approximate it as a point particle, since it is much smaller than the track itself. And this is very useful, since we can consider all the huge body as a single point, like this one. And we can describe the whole system as a single point traveling along this path. Another very important concept that we need to learn when we're talking about motion of bodies is the trajectory. And trajectory is defined as the line combining all the subsequent positions occupied by a point particle in motion. This means that if we are considering this point particle here, during its motion, it will occupy subsequent positions. And the combination of all these positions is defined as trajectory. One thing that is very important to remember is that the motion of a body, as well as the trajectory of a body, are always relative to something. And this something is the reference system. So when we are describing a body, we always need to define some reference system, a system that we use to describe the position and the motion of something. The meaning of reference system is in the word itself, so it's a system that we use as reference. In order to better understand this concept, let's say that we are looking at two cars racing. And for us, the two cars are moving along this direction with a given velocity. So we see the cars moving, and we see the landscape. The landscape for us is still. The road is still, everything else is still, but the cars are moving away from us. And this is with respect to the reference system centered on us. This means that we are considering this reference system. This is the x-axis, this is the y-axis, and the cars are moving along this direction, according to our view. But if we put ourselves, or to say even better, if we put the center of the reference system coinciding with one of the two cars, so let's say that we're considering this second reference system that we can call x prime and y prime. Well, with respect to this second reference system, The two cars are still, they are not moving, and an observer sitting on this second car, this blue car, will see the landscape and us moving away. So they will see us and the landscape moving along this direction with a velocity v that is equal in intensity as this one, but in opposite sign. So every time we're talking about motion or position of bodies, we always need to set up a reference system. We need to declare it, because velocities and positions are always relative to a reference system. And there are different reference systems that we can adopt, but the most commonly employed is the Cartesian reference system. The Cartesian reference system comprises an origin, that is almost always called with the letter O, two Cartesian axes, in this case x and y, and this is when we're talking about motions or position in a plane. When we're talking about the space, so we need 3 dimensions, we will need 3 different axes that are x, y, and z. Finally, we need a unit of measurement for the distance. In this case, we can select as unit of measurement in the plane this small square. So when we are describing the motion or positions on a plane, we will use a Cartesian reference system that needs 2 different axes, the x-axis and the y-axis, and they must be orthogonal between themselves. This means that the angle formed between the axes is 90 degrees. Then we will need an origin and a unit of measurement. Once we have all these 3 things, we have a reference system, and which is the most simple motion that a point particle can have. This is the rectilinear motion. It is called rectilinear motion, the motion of a point particle whose trajectory is a segment. This means that this point particle here, that is the simplification of our body, in this case our Cybertruck, has a trajectory that is given by a segment. So it is a straight line, and in this case we're not talking about velocities, since the velocity can change, but the rectilinear motion means that it's moving along a straight line. Now, I keep talking about velocities and speed, but how can we compute the velocity of a body? Well, we have seen that the velocity says which is the rate at which a body is changing its position. And in order to compute the velocity, the instantaneous velocity, we still don't have the tools to do that. And we will see how to do so in later lessons. But the average velocity, that one we can compute it. And the average velocity is given by the ratio between the traveled distance and the time interval spent during that motion. So the average velocity, this value here, is given by the ratio between the distance that is being traveled and the time interval needed to travel that distance. This symbol here, we've already seen it, is the delta, which means the difference between a final point, in this case the distance, the final distance or the final position, minus the initial distance. This is a variation of a quantity. So the delta identifies a variation of something. So the final distance minus the initial distance gives us the total distance traveled during a given amount of time. And this given amount of time is told us by delta t. So if we divide the distance traveled by the total amount of time taken to travel that distance, we find the average speed. And if we want to see which is the unit of measurement of speed, we just need to compute this ratio, because the unit of measurement of distance is the meter. And the unit of measurement of time is the second. And we can clearly see that the unit of measurement of speed is meters per second. If a point particle is moving at a constant speed following a rectilinear motion, we get the most simple motion possible, that is the rectilinear uniform motion, which is the motion of a point particle that moves along a line with constant velocity. So if we have a point particle that is moving along a straight line with constant speed, we have a rectilinear uniform motion. That is the most simple possible that we can have all over in the world. I know that these concepts can seem kind of confusing at the beginning, but they are much more easy to understand with exercises that we are going to do right now. But first, just a simple recap. We recalled what is a point particle, and we have seen how to describe a point particle in motion. We have learned the concept of trajectory, that is that line combining all the subsequent points occupied by a body when it's moving. We have seen what is a reference system, And we have learned that the description of motion or positions is always relative to the reference system that we are considering. Then we have seen the Cartesian reference system, that is the most commonly employed, for which we need two different axes that must be orthogonal between themselves when we are considering the plane. We need an origin and a unit of measurement. We have seen the rectilinear motion and the rectilinear uniform motion when we add a constant velocity. And then we have seen how to compute the average velocity of a body. That is the ratio between the distance traveled and the time needed to travel that distance. Now, let's use what we have learned to solve two simple exercises. The first one says, a motorcyclist covers the first 5 kilometers of his journey at 15 kilometers per hour, and the next 9 kilometers at a constant speed of 45 kilometers per hour. How long does it take for the first stretch? And for the second, which is the average speed of the entire journey? Let's first sketch this problem. We have a biker. And he's doing a journey. This is the starting point and this is the final point. So we know that he covers the first 5 kilometers up to point C with an average velocity of 15 kilometers per hour. And then he covers the next 9 kilometers at an average velocity, you can call it number 2, of 45 kilometers per hour. So how long does it take for the first stretch? So we know the equation to compute the average velocity, that is the variation of the distance divided by the time interval needed to cover the distance. In this case, for the first stretch, we know the average velocity, we know the distance that the biker travels, that is 5 kilometers. We just need to compute the time needed to cover the distance. And we just need to use the inverse formula. That is very simple. That says that the time interval is equal to the ratio between the distance traveled and the average velocity. So for the first stretch, we know that the time interval is equal to 5 kilometers divided by 15 kilometers per hour. And this is equal to 0.33 hours. And if we multiply this value by 60 minutes in an hour, we get that the time interval for the first stretch is equal to 20 minutes. Now for the second stretch, the equation is the same. We only need to change the values. And this is 9 kilometers, the distance traveled in the second stretch, divided by 45 kilometers per hour. And this is equal to 0.2 hours. And also in this case, multiplying it by 60 gives us that the time interval needed to cover the second stretch is equal to 12 minutes. So how long does it take for the first stretch? 20 minutes. And how long does it take for the second one? 12 minutes. And this answers the first question. While for the second one, it asks us which is the average speed of the entire journey. Well, in this case, we know that the average speed is given by the ratio between the distance traveled and the time needed to travel that distance. So the total distance is 9 kilometers plus 5, so 14 kilometers total, divided by the total time needed to travel that distance, which is 20 minutes plus 12 minutes. That is 32 minutes, or 0.53 hours. 0.53 hours. So the average velocity of the entire journey is given by this ratio and is equal to 26.41 kilometers per hour. And this value of the average velocity replies to the second question. The second exercise instead says, the speed of light in vacuum can be approximated to 300,000 kilometers per second. Proxima Centauri, the star closest to the Sun, is 4.22 light years from the Earth, where a light year is the distance traveled by light in a year. How many kilometers is Proxima Centauri from the Earth? In order to solve this problem, we just need to use the very same equation that we just used. So the average velocity is equal to the travel distance divided by the time interval needed to travel the distance. So if we are considering light inside vacuum, since between Proxima Centauri and the Earth there is only vacuum, in order to travel that distance in vacuum, and we already know at which speed, the average speed of light in vacuum, that is given by 300,000 kilometers per second. And we also know how long does it take for the light to travel that distance. So we know delta t and the average velocity. We just need to compute the distance between the Earth and Proxima Centauri. This means that the average velocity is 300,000 kilometers per second. And this is equal to what we are looking for and the time needed to travel the distance, that is 4.22 years, since light moves at a constant speed, the speed of light, and it takes 4 years, more than 4 years, to reach the Earth. Now, the distance in kilometers will be given by the product between the average velocity and the time needed to reach the Earth. That is 4.22 years. So now we just need to convert years in seconds. 4.22 years is equal to 4.22 times 365 days every year times 24 hours every day times 60 minutes every hour times 60 seconds every minute. So we can simplify. This was year, and we get seconds. This value is equal to 133 times 10 to the 6th power seconds. And now we can substitute this value here into this equation to find that the distance between the Earth and Proxima Centauri is equal to 4 times 10 to the 13th kilometers, which is a lot. So next time your mom asks you, how far is Proxima Centauri from the Earth? You can tell her, well, it's 4 times 10 to the 13th kilometers, or a lot, which is basically the same. And this is all for today. See you next lesson.